Welcome back to Physics 141 online. Today we'll begin our very brief survey of gravitation. And by this, we're now extending our treatment of the force of gravity to deal with the more general situation when we're talking about the motion of objects that are very far away from the Earth's surface. We already have expressions for the force of gravity and the potential energy due to gravity for objects that stay near the Earth's surface. And by that we mean where their height above the Earth's surface is very small compared to the radius of the Earth. But if we're interested in space travel and rocket problems, then we have to extend our treatment of gravitation. And to do that, we need a little history lesson. So, Kepler was the first one to discover, before the time of Newton in 1609, that planets orbit the Sun in elliptical paths, although for some of the planets, like Mars and the Earth, the orbits are not that far from being circular. Then, from that initial discovery, about 80 years later, Isaac Newton showed, and he was kind of working backwards. He knew the elliptical shape of these orbits, but he showed mathematically, through his invention of calculus, that an elliptical orbit could only occur if the force of the Sun pulling on the planets was inversely proportional to the square of the distance between them. And thus, this gave rise to what is called Newton's universal law of gravitation. So what this means is the force is proportional to the product of the masses that are involved, and here this might be the Sun and the Earth. It's inversely proportional to the square of the distance, and the proportionality constant that tells us how strong the force is a fundamental constant, g. And that g, through very, very careful measurements that have been made more and more precise over the years, has the value 6.67 times 10 to the minus 11, and the units we can figure out if we were to just take the law of gravitation and solve for g, we would see that the units would be newtons meters squared over kilograms squared. Now, it's important to realize that the distance r that appears in this law is actually the distance between the centers of these objects, and that becomes important if we're talking about large objects like the Earth or the Sun. So that's the law of universal gravitation. The significance of g, it's really the first fundamental constant of nature that we've encountered in the course so far. Little g is related to it, but little g is not a fundamental constant, as we will see in a few minutes. Big G was first measured carefully in 1798 by an English scientist named Henry Cavendish, and it's a measure of the strength of one of the four fundamental forces of nature, gravitation. The value of g is really important because it influences what happens on a very large scale throughout the universe. Not only the structure of galaxies, but also the inner dynamics of stars. A star is basically a big collection of hot gas molecules, mostly hydrogen, and they're bound together and held together gravitationally. And as a big bundle of hydrogen atoms attract one another, they slowly contract. And so the hydrogen atoms get compressed and brought closer and closer together until they come close enough, and the force of gravity, of course, as they get closer, the force of gravity gets bigger, and eventually they come close enough to trigger nuclear fusion reactions. Those fusion reactions liberate huge quantities of energy, and that stabilizes the star from contracting, so it reaches kind of a steady state situation, and that's the situation that our Sun is in. And it will stay that way for several billion more years until all the hydrogen is exhausted. And if you want to find out more about what happens after that, you should take our introductory astronomy class. So what's the connection between big G, the fundamental constant, and little g that we've been using to measure the acceleration that an object has near the Earth's surface? So imagine that we have an object of mass m that is sitting on the Earth's surface, a distance from the center of the Earth equal to the radius of the Earth, and the Earth has mass me. So if we apply our expression now for the more general expression for the universal law of gravitation, that measures the force between this mass and the Earth, and if we set that equal to mg, which we've been using in our study of objects near the Earth's surface, we see we can solve for little g, and it equals the fundamental constant times the mass of the Earth over the square of the Earth's radius. So we see where little g comes from. It's not fundamentally an important quantity, because if we were to calculate this on the surface of the Moon or the surface of other planets, we would get different values. But big G is the important fundamental parameter that tells us how strong that force is between any two masses. Notice that if we were to plug in values measured for g and also measured for the Earth's mass and radius, we get an expression that would be 9.83 meters per second squared, which is very, very close to the value that we measure if we measure the acceleration of objects near the Earth's surface. This treatment here does not account for the slightly non-spherical shape and non-uniform density of the Earth, and also the fact that the Earth rotates. And so it's only approximately what we measure, but you can see it's in fairly good agreement. So that's where little g comes from and how it's connected to the more fundamental gravitation constant, big G. Now let's use this fundamental law of gravitation to calculate a new expression for gravitational potential energy. I'll remind you first of all where the expression mgh comes from that we've been using for objects near the Earth's surface, and then we'll extend that to the more general case of an object that's going to be launched from the Earth's surface, or the moon, for example, that's far away from the Earth. So I'll remind you again, the definition of potential energy difference when we move an object from one place to another, that's equal to minus the work done by a conservative force. Gravity is a conservative force, and what that means is the work it does only depends on the initial and the final position. And so if we were to calculate this work done by the gravitational force and then take the opposite of that, that is how potential energy is defined. So the most general case, if we had a force that was changing, we would have to take the dot product of F dotted into this infinitesimal displacement vector dr, and then do the integral and evaluate it between the initial and final positions. For an object near the Earth's surface, this is actually very simple. We don't really have to do the integral because the force is not changing. So if we have an object at the Earth's surface and we're going to raise it up a distance h in the j direction, the y direction, recognizing that the Earth's gravity, the weight of the object, pulls down with a force minus mg in the j direction, then we can easily evaluate this work by using the expression negative f dot delta r, where delta r is the displacement of the object as we raise it from the Earth's surface to a point that's a distance h above. So the minus sign comes from the definition of potential energy, and now this dot product is easy to evaluate. Actually, it's the magnitude of the force times the magnitude of the displacement times the cosine of 180 degrees. So the minus sign gets canceled out. The dot product gives us minus minus mgh, and then minus a negative is a positive. So we see that when the object starts at the Earth's surface and is raised a distance h, the potential energy change is mgh. So we've been using that, and formally then we would say that the gravitational potential energy is equal to some constant u0, the initial potential energy, plus mgh. And u0, we set that equal to 0, and we just choose it to be at a certain convenient reference point. But it's an arbitrary point that defines the zero value of potential energy. So we now know that we can't necessarily use this formula here for the gravitational force of the Earth if the object is going to be far away from the Earth's surface. So let's now do the calculation for the general case. Here's the Earth, or some big object m. Then we have a smaller mass m that's going to be raised a certain distance, and we'll just take it to be some r0 value, and then it's going to go up to some r final value. R is being measured, if we're going to use the universal law of gravitation, r is being measured from the center of the Earth. And notice here, since we want the force on the object that's at this distance r away, it's in the negative r hat direction. R hat is the unit vector that just points away from the center of the Earth. So for this mass, the r hat vector is pointing upward in this picture, and that means that the force is pulling down, so the force is in the negative r hat direction. So if the object is initially at a radial distance r0 and we raise it to a final distance r, and that's indicated by this arrow, we can calculate the change in potential energy, once again minus the integral from the initial position to the final position of this quantity f dot dr. And looking at the vector expressions for f right here, dr is pointing in the r hat direction. It's the infinitesimal change in the radius as the object is moving from its initial to its final position. So dr is upward, r hat is downward, the force is downward, and so when we take that dot product, we're going to get a negative quantity because the angle between them is 180 degrees. And it's just the product of the magnitudes, g big M little m over r squared times dr, and then it's going to have a minus sign. There's already a minus sign due to the definition of the potential energy function, and so minus a negative is a positive. So the integral that we have to do is gmm, those three are all constants, so those easily come outside the integral, and what we're left with is r squared dr. And you're probably at a point in your calculus class, or soon will be, where you can do that integral. We've done simple integrals like this before. It's a little bit confusing when you see that the variable is in the denominator, but let me just show you how to handle this easily. First, we pull out gmm outside the integral, and so we write 1 over r squared as r to the minus 2 power. That makes it easier for me to take the next step, which is to evaluate the antiderivative of this function. And remember, the simple rule for these power type of functions is the magnitude, the size of the exponent increases by 1. So negative 2 plus 1 is negative 1, and then we divide by that new exponent, negative 1. Okay, so the integral of r to the minus 2 is r to the minus 1 over negative 1. And we express it like this. The gmm is just a constant out in front. We have to now evaluate it between the upper and lower limits, and if I write this now with, since it's r to the minus 1, it's just 1 over r. And then the minus sign comes out in front. So what we're left with is minus big G, big M little m over r, evaluated between the two limits. And since what we're calculating is the change in the potential energy, I'll write it like this, change in potential energy, and the very last step is just minus gmm over r, and then subtracting negative gmm over r0, and minus a negative is a positive. So this is our general expression for the change in potential energy for an object that's moving not necessarily near the Earth's surface, but between two positions, a distance r and r0 away from the center of the Earth. Usually, just like before, we have a choice of where we want the potential energy to be 0. Usually we choose that point at r equals infinity, so that u0 would be 0, because at r equals infinity we would have 1 over infinity, so that second term would go to 0, and therefore we're left with the gravitational potential energy with this choice of the initial value, or the 0 value. We write the gravitational potential energy as minus big G, big M little m over r. So it might seem a little bit odd that we would choose the 0 value to be at infinity, but we'll see a little bit of a reason for that as we work out an example in just a minute. So what this means is that the potential energy function is, if r goes toward infinity, then it becomes 0, just like we said. That's our choice of where we're going to measure it from. So our last point in this introductory section is just to now discuss, having learned about gravitational potential energy, let's figure out how we can write down energy for satellite motion, for the motion of the moon around the Earth, or the Earth around the sun. So the total energy, if we've got a mass m that's orbiting in some path around another mass m, and we assume that big M is so large compared to little m that we can treat it as being essentially at rest. There is going to be a little bit of a motion of that, but we will ignore that as a first approximation. So the total energy, which, if the only forces acting on these two are from one another, the total energy of this orbiting mass should be approximately conserved. So K, the kinetic energy, and U, the potential energy, we add those together, we get 1/2 mv squared, minus, because the potential energy is negative, minus gmm over r. So that's the total energy of the system. And here's the important point, and this is just a qualitative way of understanding satellite motion. If the satellite remains bound to the planet in an orbit like this, which means it comes back over and over and over again and repeats this same orbit, then its energy is less than 0. How do I know that? I know that because if E became really, really large, if E, let's say initially, if there was an orbiting satellite around a mass, so I'm asserting that its energy is less than 0, if we increased its energy, then what would happen is it would make the distance away from the planet to be larger and larger. And at that point where that value r gets huge, gets really, really large, that means the potential energy would go towards zero. And at that point, then, the satellite velocity would be really, really small. And so if we imagine increasing the energy by increasing the distance, then eventually, since it starts off negative, eventually we would get to the place where the total energy would be exactly equal to zero. And that would mean that the kinetic energy would be zero and the potential energy would be zero. So the borderline case for an object that gets, whether to tell you whether it's bound or whether it's free, is that situation where it's infinitely far away but it's not moving. So we can have, and that's of course where the energy is equal to zero. If the object is bound, then its potential energy is negative and its kinetic energy is positive, but not so large for it to reach a total energy of zero. On the other hand, if the satellite escapes from this planet here so that it's not making a closed orbit, then it can reach infinitely far away and still have some velocity so that its total energy would be positive. And we would say then that it's actually escaped from the gravitational pull of mass big M. So that may be a little bit confusing, but if you think about it, the important point is that when the total energy is less than or equal to zero, we have a bound system, and that means a closed orbit. So let's do a very simple calculation based on that idea. We can use this idea that a bound system is where E is less than zero, and then an escape situation is where E is greater than zero. We can use that to calculate the minimum velocity that we need for an object that's initially at the Earth's surface, like a rocket, to escape from Earth's gravity and thus never to return to orbit the Earth. And we're going to neglect the effects of atmospheric friction here, which are significant but difficult to calculate. So this will be kind of an approximation. So what's the condition that we want to reach? If we light off a rocket at the Earth's surface and it takes off, we want to know how much speed it has to have initially in order to escape from the Earth's gravity. And of course, in a real situation, when there's liftoff, a rocket starts from rest, and so it builds up to this escape velocity that we're going to calculate over the course of its ascent. But eventually, when it's not too far off the Earth's surface, it has to reach a certain minimum velocity in order to escape. Otherwise, if it's below that velocity, it'll go up and just come back down to Earth or orbit the Earth. It won't actually escape. So the condition for escape, like we just talked about, is where the initial energy, the energy that it has when it's first launched, is greater than or equal to zero. Right? Because once again, that would mean that it could get infinitely far away, where the potential energy goes to zero, and either be at rest, which is kind of the borderline case, or still have some potential energy still have some kinetic energy because of the fact that it's still moving. So here is the condition. And so what we can do is simply solve for V initial from this inequality here. And when we solve for it, we end up with V initial equal to the square root of 2g me over the Earth's radius. And so we'll call that the minimum escape velocity, because if the velocity initial is greater than this, of course it escapes as well. Notice that the mass of the satellite itself cancels out, and so this speed is not affected by how large the rocket ship or the satellite is. So if we evaluate this by plugging in values for g and the mass of the Earth and the radius of the Earth, we get 11.2 kilometers per second. And this is called the approximate escape velocity for an object that's initially on the surface of the Earth. So here's the question I'll leave you with, and we'll pick this up in class, because this is a practical one. If you're actually going to build a facility that launches payloads into space, it turns out that if we understand escape velocity and we understand a little bit about the dynamics of the Earth, we can figure out what's the best direction to launch rockets from on the Earth's surface, and at what location should you build your launch facility. So think a little bit about that. Basically, The key here is to realize that the Earth is not at rest, but the Earth rotates. And because of the Earth's rotational motion, there are certain places on the Earth's surface that are going to be more advantageous to build a launch facility than others. I hope this has been a helpful introduction, and I will see you in class.